Hey, everybody. Okay, so um, was texting with one of the friends of the program today, and one thing he raised was something I was talked about in one of my videos I posted either yesterday or the day before, talking about the lumpers versus the splitters, and how if you have too many categories or too many variables that or too many personality types, you get into a situation where it's just statistically impossible to have any sort of reliable data that anybody can believe. And he was asking, can you sort of walk through that and provide some examples? And I thought, okay. And and I think the best thing to do is just kind of do this through Chat GPT. And so for those INTPs out there that are interested in this, and maybe even the ISTJs, feel free to follow at home. You can use probably any sort of Chat GPT type AI system. I'm going to just use Google's search mode, their AI search mode that they just put out. But I'm sure this will work for anything. And just by real quick explanation, and it's been years since I've had to teach this stuff. So for those of you who are sort of statistics experts or research experts out there, feel free to correct me and tell me if whatever I'm saying is wrong. But I'll at least be able to show the math that backs up my claims in a second here. But one of the things that I raised in the earlier video is, one of the problems with the MBTI and just sort of personality types in general, where you're trying to figure out if somebody an ISTJ or an INTJ, you're trying to put them in a bucket. In statistics, we call it binning. You're trying to put them in a bin, right? And these are discrete variables where you're putting they're in one category and at the exclusion of all other categories. They can't be sort of half in one category, half in the other, or one quarter in one category, three quarters in the other. You're either an ISFJ or something else, right? Um, and I'm obviously ignoring all the ambiverts and all that kind of stuff. So let's just go with sort of the traditional. You got to be in one of the 16 type categories. And when you do that in statistics, it causes all kinds of weird problems. And I'm going to walk through one of them. There are others, but the one I'm going to talk about today is Bayes' theorem. And it's, to me, Bayes' theorem is the thing that humbles you the most. If you fancy yourself a researcher or an intellectual of any type, or even a doctor or a lawyer, where your job is to make decisions and figure out whether or not somebody's in a category or not, this will humble you. And it shows you just how small changes in the number of groups and whatnot, or in the underlying probabilities, make huge differences. And really, the best way to to talk about it or to demonstrate it is just to show you some examples here. Um, so I'm going to be typing this in, like I said, to Google AI. You can play along at home and sort of mess around with some of the variables and the functions, and you'll see what I'm getting at. But ultimately, you want whatever Chat GPT system you're using is to walk through a Bayes theorem analysis. If it's doing something other than Bayes theorem, then tell it to do Bayes theorem. Okay, so I'm going to start off with a real simple example that doesn't really have to do with personality types, but I think it's a good example that I like to use, or did like to use when I had to teach this stuff, to sort of show the magnitude of Bayes' theorem and sort of the power of it. Okay, so let's assume, and I'm going to be typing this in while I talk, so I apologize for the awkwardness here. So assume Mike says that he's a Leo. Zodiac sign, and assume that 1 out of 12 people in the population are Leos. And I understand it's not exactly 1 out of 12, but just for the purposes of the example, let's just say you have an equal probability of being any one of the 12 zodiac signs, okay? So Mike says he's a Leo, zodiac sign, and assume that 1/12 of the people in the population are Leos, and further assume that Mike says that he is 99% sure that he is correct. Okay. Now, what is the probability that Mike is actually a Leo? Okay. All right, so I'm going to read it again, and then I hope this is going to actually generate what I think it's going to, but we'll see. Okay, so here's the problem again. Assume Mike says that he's a Leo zodiac sign, and assume that 1/12 of the people in the population are Leos. So 1 out of 12 people are going to be a Leo. Again, we're just assuming that. Further assume that Mike says that he is 99% sure that he's correct. So he's very, very confident that he's a Leo. 99%. That's about as confident as you can be. Okay. Very unlikely that he, he thinks it's very unlikely that he's anything else other than a Leo, right? Okay. So what is the probability that Mike is actually a Leo? So we're gonna look at it. Now it's doing its little thinking. Let me see what it comes up with. Okay. So good. Okay. So it did what I was hoping it would do. Okay, it's applying Bayes' theorem here. Okay. And if you do this through one of the chat bots, it'll sort of lay out the math behind Bayes' theorem in case you're curious. But it's basically just playing with the probabilities. So let me back up. So if I tell you that Mike is 99% sure that he's a Leo, and then I ask you what's the probability that Mike is actually a Leo, the natural instinct, and there's plenty of data to support this, most people will just say, well, it's 99%. He's 99% sure that he's a Leo, so there's a 99% chance that he is a Leo. But aha, this is where Bayes' theorem comes in. You have to take into account the fact that there's a 1% chance that he's wrong, okay? And because there's this 1% chance that he's wrong, then you have to look at the probability that he's just randomly going to be a Leo versus anything else, right? So put it another way, if if you're wrong, it's that 1% time that you're wrong, the 1 out of 100 times you're wrong or Mike's wrong, then there's an 11 out of 12 chance that he's not a Leo, okay? So that 1% sort of inflates because of the low probability, just 1 out of 12, that he would just randomly be correct, even though in general he thinks he's 99% sure, but maybe he is wrong, but he's not wrong, right? But there's only a 1 out of 12 chance that he's wrong, but then he ends up still being a Leo anyways, right? So in other words, there's that 1% chance that he's wrong, and then if he is wrong, there's an 11 out of 12 chance that he's something else, okay? And so you have to combine those probabilities, so to speak, and through Bayes' theorem, and it's a pretty simple formula, but a very important concept underlying it. So here's the answer. So if he has 99% certainty and Leos are only 1 out of 12 of the population, Bayes' theorem combines this information for a more accurate assessment. And that is that the real probability that he's a Leo is 90%, 90%, not 99%. Okay. So you might be thinking, okay, big whoop. He's still 90%. There's still a 90% chance that he's right. Okay. So let's say Mike isn't as confident. So same problem. However, assume that Mike says that he's 75% sure that he is a Leo. Okay, so he's not as confident that he's a Leo. He's not as confident about when exactly he was born or when the Leo cutoff dates are or whatever, So now he's only 75% sure. He's still kind of sure, but only 75% sure. And Leos are still randomly only 1 out of 12 of the population. Okay, so it's going to do its little thinking here again. Okay, so lays out the math here. And so now, because he's only 75% sure, the chances that he's actually a Leo is 21%, 21.43% to be precise for you INTPs out there. So he's still pretty sure, 75% sure, but the chances that he actually is a Leo when he says he's only 75% sure goes down to roughly 20%. Okay. So, as your margin of error or confidence rating goes down, the probability that you're correct goes way, way down. Okay. So now let's just take it to the extreme. Same problem, but assume that Mike says that he is only 25% sure that he is a Leo. So in other words, he actually kind of thinks it's more likely than not that he's a Leo in some respects, right? He's only 25% sure that he's a Leo. And that takes you down to 2%. Okay. Same problem, but assume that Mike is only 50% confident that he is a Leo. So, he's like 50-50, I'm a Leo, kind of taking a guess. That's what most people would say, it's 50-50 chance I'm right or I'm wrong. So if he's only 50% confident that he's a Leo, then there's only an 8.33% chance that he's correct. Okay. So again, there's a 1 out of 12 chance that he is a Leo just by pure random chance, right? Again, assuming that all the zodiac signs have equal distribution, which is, I realize isn't true. So he's got a 1 out of 12 chance, but he thinks it might be a Leo, but I'm really not sure. I'd give it 50-50 odds. I'm 50% confident. That takes the probability that he actually is a Leo all the way down to 8%, right? And the normal, if he was just sort of randomly guessing, what is 1 divided by 12? If he was just randomly guessing, then it'd be like, yeah, it's basically an 8%, right? So he's basically saying 50-50, I'm kind of randomly guessing, comes out to be about 8% chance, which is 1 out of 12, okay? So hopefully you see where I'm getting at, right? So you not only have to take into account the accuracy of the test, but also what's the likelihood in the general population, okay? And the more that the lower the probability is in the general population, it takes your numbers way down. And so let me give you some examples that maybe make sense in the personality type test or world, okay? And again, you can follow along with me on your own chat GPT device of your picking, of your choosing. Okay, so now we're going to do MBTI. Okay, so assume that I score as an INFJ in the MBTI personality test inventory. Further assume that there are 16 type categories that exist in the MBTI personality inventory framework. Further assume that there is a 1 in 16 chance. Wait, hold on. Let me back up. Further assume that 1 out of 16 people in the population are INFJs. So again, we're just going to assume that there's an equal number of all the different 16 personality types. I realize that's not the case. For right now, let's assume there are, and then we'll give examples of what happens when you actually take in real data and real, probabilities that somebody's, an INFJ versus an ISTJ. But we'll do that in a second. Okay, so for right now, we're just assuming that every type is sort of equally distributed, that there's the same sort of percentage of people in each type. Okay, so you have a 1 out of 16 chance of being an INFJ. Okay. Further assume that the MBTI test that I took is correct 99% of the time. Okay. So if an MBTI test, it's very, very good. It's 99% of the time, it tells you exactly what you are. And we all know that that's probably not true in reality, but we're going to give it as much of the benefit of the doubt as we can, right? It can't say 100% because that just completely gets rid of all of this. But you can say 99%, and every once in a while somebody fills in the wrong bubble or there's some sort of mistake, So there's a little bit of error there, but 99% of the time they get it. You get the right type when you take the test, okay? And there's a 1 out of 16 chance that just randomly that you're an INFJ. So what happens if you take the test and you score as an INFJ? What's the probability that you really are an INFJ? Okay, it's doing the math. Hopefully I prompted it right. Okay, Bayes' theorem, yeah, okay. So even with a 99% accurate test, okay, so I've already sort of explained sort of what's going on here in the previous example. So here, the probability that you are actually an INFJ, given your test result and the assumptions, it's approximately 86.84%. So again, the test has a 99% chance of being accurate. 99 out of 100 times, it gives you the right result. Tells you you're an INFJ when you actually are an INFJ. But there's that 1% chance that it gives you the wrong result. And because you only have a 1 in 16 chance of just being randomly correct, that means in that 1% time where it's wrong, then there's a 15 out of 16% chance that, or 15 out of 16, chance that you're something else other than INFJ. Okay. And so when you combine those two together, then really, when you take the MBTI, even if it's 99% accurate all the time, you can only be, you're only the probability that you actually are an INFJ is only about 86, 87%. Okay. And that's giving a lot of benefit to the MBTI, right? So let's do sort of a more likely example and just say, assume that the MBTI test is correct 85% of the time. Again, we're probably being pretty generous in saying that it's correct 85% of the time. And we're still saying that INFJs or all of the personalities are equally represented in the population. So there's a 1 in 16 chance just you're randomly an INFJ. Okay. So 85%, of chance of being correct is the test. That takes, so get this. I mean, this is the power of the Bayes theorem. So we moved it from a 99% chance or 99% confidence level. So 99% of the time, the MBTI test is right and gives you the correct result. And we move that down to 85%, so that now only 85% of the time, the MBTI is correct and gives you the right result. And that other 15% is just error, right? For whatever reason. It's not asking the right questions. The person isn't answering, truthfully. You have a bad, administrator who's just not paying attention. You have a bad test taker who's not taking it seriously, whatever. You got that 15% cushion, and 85% of the time it's correct. That's probably relatively okay, for a psychological exam. It's not great. You'd certainly want it to be a lot better than that, but, it's okay. Okay, get this. The chance that you're actually an INFJ is 27.42%. Okay. So even in the situation where the test has 85%, it's correct 85% of the time, you score as an INFJ, there's really only a roughly 27% chance that you actually are an INFJ. Okay. This is why academia does not mess around with the MBTI, right? Because as soon as you get out of as soon as your margin of error starts increasing, the probability of getting a correct answer just plummets. Okay. And this is assuming that INFJs and every other personality is just a 1 out of 16 chance, that everybody has an equal chance, that the population, is distributed equally among the different types. And we all know that's not true because INFJs are special, and we really are only 1.5% of the population. So let's do that, something more accurate. And let's go back and give the MBTI its due and say that it's correct 99% of the time. Okay. 99% of the time, the MBTI, if it says you're an INFJ, then it was correct. And, but 1% of the time it's incorrect. Okay. So same problem. However, assume that the MBTI is correct 99% of the time. And further assume that only 1.5% of the population is an INFJ. What is the probability that I am an INFJ if I score as an INFJ on the MBTI test? Okay, so again, we're saying 99% accuracy rate for the MBTI test. It's correct 99% of the time. 1% of the time it's incorrect. But only 1.5% of the population is an INFJ. And that sort of goes along with what the actual numbers are out there when they do the research. Usually INFJs come out to about 1.5% of the population. Okay, so let's see what this gets us. Okay, so using 99%, accuracy for the MBTI test, and only 1.5% of the population is an INFJ. If I get a score as INFJ on the MBTI, then the odds or the probability that I actually am an INFJ is only 60%. It's a lot better than the 27% we had before, right? But it still is only 60%. So you really are almost just guessing. Even with a test that is 99% accurate, right? But because there's so few INFJs in the world, only 1.5%, if you happen to be the one person out of 100 where the MBTI gets your score wrong, then there's only a 98.5% chance that you're something else other than an INFJ, right? There's only, so if you're that one person where the MBTI scores you incorrectly, then there's only a 1.5% chance that you actually are an INFJ, right? Just randomly. And so you combine again those probabilities. And so even if I score as an INFJ on the MBTI, I can only say with 60% assurance that I am an INFJ. Okay. So again, this is why academia doesn't like the MBTI. This is why they don't like dealing with categorizations and discrete variables, because it lends itself to this problem. You can't be 50% in one category and 50% in another. That would increase your odds of being typed correctly, but that's just not the way it goes. Okay. So now that I've got that in your head, let's talk about other typology systems that are splitting things up into more and more categories, right? And what's the probability? You can do the math in your head probably at this point, but what's the probability that if you score as an INFJ under their system, that you actually are an INFJ or whatever they categorize you as? Okay, so let's pick on objective personality. 512 types. Okay, you can see where this is going. And let's just assume again that it's equally distributed. So there's equal number of people in each of the types. And that's giving them the benefit of the doubt. That's being the least conservative with the numbers. We're giving every type, of the 512 categories, the best probability, right? So let's say you have 1 out of 512 chance of being a particular type just randomly, right? Okay. Let's also assume that the people giving the test have it nailed down to where they're correct 99% of the time. Hell, let's do 99.99% of the time. Okay. Where do you think we're going to end up here? So I'm going to type this in, bear with me. Okay, new problem. Assume that I took a personality test and scored as a alpha 1. Okay, whatever. We're just making a name up here. Further assume that 1 out of 512 people in the population are an alpha 1. Further assume that the chance that the test was correct is 99.99%. Okay, so you have the best scorers in the world. You have the best possible exam, people who are scoring you, right? Let's just assume that their system works beautifully. And it's only randomly somebody, answers the wrong question or fills in the wrong bubble, or they just put the wrong piece of paper in the wrong pile or whatever. But it only happens like 0.1% of the time. Okay, 99.99% chance. Let's see what the math does. Okay, so the probability that you actually are an alpha 1, given your test result and the assumptions, is approximately 95.13%. Okay, so if they are 99.99% correct all the time, even if it's just 1 out of 512, chance, then there's a 95% probability that I actually am an alpha 1. Okay. So let's say that they're not 99%, 99.99%. Same question, but assume that the test is correct 99% of the time. Okay? So we're going from 99.99% to just 99% of the time. So even if it's 99% accurate, only 1 out of 100 times they type you incorrectly. If you get a score of alpha 1, the chances that you actually are an alpha 1 is 16%. 16%. Like, that's the level of confidence that if you go through, this test and come out a certain type, and again, this is assuming that all types are equally represented across the population, right? There's a 16% chance that they're right. Okay. Okay. So let's just play around with the numbers again. So same problem, but assume that 25% of the population is an alpha 1. I'm not sure if I'm doing this correctly, but let's see what he goes is. Yeah. So if it turns out that, like, there's one type out of the 512 where 25% of the population is that type, it's an alpha 1, then your probability of being correct goes back up to like 97%, right? But you need, out of all those 512 types, you need 25% of the world to be only one of those types, right? So right. Okay. So this is why when you have all these variables that are supposed to be checked off, or all these different categories that you could fall into, the numbers just completely fall apart, from a statistics standpoint. Okay. Where you just can't rely on, the result, even if they're correct 99% of the time, right? It's just that 1% time that they're incorrect. And the fact that it's so unlikely that you are that type, just by random chance, it takes the numbers the overall probability of you actually being an INFJ or an alpha 1 or whatever you want to call it way, way down, to where it's just not even worth, discussing. And again, this is the problem with, discrete variables. I don't want to belabor that point because there's all sorts of complicated math behind it, which frankly, I don't know, but some statistician can walk you through it if you're curious. But it's just that you're either in one category or you're in another category, and there's a probabilities associated with being in those categories. Okay, so that's a little bit why academia doesn't really deal with the MBTI. There's also other reasons. I mean, MBTI is sort of its own corporation, and they like to keep their results close to the vest, that kind of stuff. But so you have to just take all this stuff with some grain of salt, right? Like I said at the beginning, the Bayes theorem will humble you if you are a researcher or you're trying to do any sort of research or statistics or just sort of explain the way the world works in this way. And so for those of you out there, doing your own typing, keep in mind, even if you're correct 99% of the time, like God bestowed upon you, this incredible MBTI radar where like exactly what somebody is, just by looking at them for 30 seconds, and you're correct 99% of the time. The chances that you accurately type somebody, because there's that 1% chance that you're wrong, that 1% explodes into, like you're really only accurate 20% of the time, 30% of the time, 40% of the time. You're more, if you guess that somebody's an ISTJ, you're more likely to be right because there's more ISTJs out there or ISFJs. But if you guess that somebody's an INFJ, then it's very likely that you're wrong, right? Even if you're correct 99% of the time, right? So it's a very counterintuitive way of thinking about probability, but the math works out. It really is the way the world works from a probability perspective. It does sound sort of counterintuitive or contradictory for me to be saying you're right 99% of the time, but anytime that you do it, you're really only going to be right. You really only have a 50% chance of being correct. I get that seems to not make sense, but it is the power of the Bayes theorem, right? And it is what Bayes theorem is all about. And if you are interested in it, I would recommend just watching random YouTube videos on it. There's tons of them. But the take-home message, of course, two take-home messages. Number one, all of these systems, the socionics and what do they call them, the dichotomies or whatever, where there's like 40 dichotomies and all this stuff, the more variables you add to the equation, and the least, and then the lower the probability is that somebody is just randomly that type or randomly falls into this category, the harder and harder it is to be confident that when they score as such and such type that's accurate, that actually is what they are, even if it's just a 1% chance that you're wrong, right? That's the power of the Bayes theorem, and that's what's so humbling about it. And so I'm going to put a pin in this because I'm going to come back to sort of the model issue, because I do want to admit to something that, or let me come back to it. The other lesson, though, to get out of this is no matter how good you think you are at typing somebody or typing people based off of watching YouTube videos or interviews or typing sessions or whatever, the chances that you are actually correct are very low, okay, or much, much lower than you think they are, okay? And the more you understand Bayes' theorem, the more you'll understand that point. And so it will hopefully, if you take it to heart and and really understand the math behind it and the logic behind it, it will hopefully sort of temper people's, you know, um, how well they, like their self-assessment, like how well they think they, or how good they think they are at typing people. Now, I'm not picking on anybody in particular. It's just I've been in this typology community for 20, 25 years, and there's this sort of waves of people that sort of come in and out that they it's the the um the Kruger effect, Dunning-Kruger effect, where they learn a little bit about it, after a couple of years, and they read a couple of books, and they read the wiki pages on socionics, and they think they got it all figured out. They're usually INTPs, and they're very smart people, and they got it all figured out, and then they come swooping in, telling everybody that they're wrong. And I've just seen waves and waves of it come and go over 25 years. And I would just, and I even saw it when I was in academia. I mean, you see it everywhere. It's not just the typology community. Bayes' theorem hopefully humbles you, right? And at least teaches you that no matter how good you are, if there's a 1% chance that you're wrong, that 1% chance just blows up, especially in this typology community. If we only had 4 categories, then, your chances of being right would be that much better, right? But we got 16, and they're not equally distributed among the population. So, point being, if again, if, to the extent that you're betting the house on typing somebody, and, God himself comes down and tells you whether you're wrong or right, guess ISFJ. Just go with ISFJ or ISTJ, because you're more likely to be right just guessing ISFJ or ISTJ than you are just with your own sort of take in assessment on the person, right? Just from a pure statistical standpoint. This is sort of the statistics that backs up the Monty Howell problem, if you've ever heard of that. It's sort of the same concept. Okay, let me get back to the models out there that are using like 512 categories or whatever. Now, from a traditional Bayes theorem statistics probability approach, it doesn't work. It doesn't work at all. I mean, I don't want to say it's laughably incorrect, but it's very incorrect. And anybody who's sort of pushing it just doesn't get the general stats behind how this all accuracy and probabilities and stuff works. Not to disparage anybody, but it's clear that they're not thinking of it in these terms. Okay, but that being said, there's an argument out there because it's in the big data world, which includes the statisticians and the actuaries and all that maybe we really don't need the traditional statistics where we're looking at everything on sort of a probability general population distribution framework, because we actually have the processing power and the data storage power to just run the data as is, right? Rather than having to make assumptions and to lump things together through various statistical things. Okay. So let me give you an example. And I've raised this talked about this on an earlier video, but it applies here too. So 20 years ago, before the big data revolution, 20, 25 years ago, if you had a company like Netflix or Amazon where they were trying to figure out, a quote unquote algorithm for you, like what to recommend, what movie should we recommend to this person, or what YouTube video should we recommend to this person based off of their viewing history, or what product should we recommend on the Amazon store. 25, 30 years ago, using traditional statistics, what they would have done is just say, okay, this person is in this general demographic, they're this age, they live in this part of the country, they're male versus female, they're white versus black, and they would break you into like demographics and then just say, okay, you know, white guys in their mid 40s in middle America love this movie. So let's just recommend that movie to him. And, and there's a good chance that he's going to like it because he fits into that demographic. Okay. And they would use traditional statistics models to do that. But now, because it's so easy to store your data and collect your data, you personally, not your demographic, but you personally. Now they can figure out what you personally would like and would recommend, right? Like what products, what movies, what YouTube videos, based off of your purchasing history, based off of your where you live in the country, what you've been watching on YouTube, what you've been searching on Google, all that kind of stuff, right? They can cater it specifically to you and they don't need to use general statistics, right? They don't need to throw you into a general demographic. So, to the extent that you have these models out there that are trying to pinpoint somebody's personality type, then and the fact that maybe you could collect the data to where you really don't have to put people into categories, everybody gets their own category in the same way that everybody gets their own algorithm on Amazon or their own algorithm on Netflix, then maybe it's okay to have all, these infinite number of types, right? If all you're trying to do is cater something to one particular person, this particular person tends to like this or that. But that's not typology. That's not like figuring out what type somebody is, what category to put them in. Okay. So if somebody's got a quote unquote personality inventory out there where they're trying to just cater to individuals or very small groups of individuals, then fine. Okay. But my sense is that it's not exactly what they're doing. They're trying to do a more complicated version of the MBTI. And the sociotics, it's certainly not what they're doing. Um, and again, they're just overly complicating things by adding more and more layers. Okay. So when you see, Nardi and other people out there in academia, coming up with the subtypes and all that, keep Bayes' theorem in mind. They think they're getting more precise, and they think they're describing the data and the world and the personality phenomenon in a more precise way. But really, what they're doing is making it more. They're making it more and more likely that they're wrong, that they're mistyping somebody, right? That when they say they are an INFJ subtype, blah, 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 with, a twist of this and a twist of that, all they're doing is making it much more likely that they're wrong, much just like infinitesimally more likely that they're wrong. And if they really wanted to sort of increase their accuracy levels, then they, should be lumping things together, making fewer groups more than more groups. And so this is kind of the classic trade-off between precision and accuracy, right? They're trying to be precise. They're trying to give you a precise reading that's more and more detailed and more fine-tuned, but they're missing on the accuracy part of it. There's this the more precise they try to get, the less accurate they are. So that's that. If there's any actual statisticians out there that want to correct anything that I've said or push me on anything, feel free. Like I said, it's been years since I've had to think about this stuff, other than just sort of randomly thinking about it when I see these typology videos. Okay. Talk to you next time. I might come back later. I've got other shit to say about other things, but we'll see. All right. Have a good night. Bye.